Assalamualaikum, we are from Group 5. We would like to present our project entitled Mini CRYOSTAT Cooling Chamber. In this project, we design and develop a simple and low-cost cooling chamber that demonstrates the basic principle of cryogenic cooling using recycled materials. Before we begin, this is our group members who contributed to this group. First, let's look at the introductions of our project. A cryostat is a device used to maintain extremely low temperature for various applications. Cryostats are widely used in scientific research and technology, especially in superconductivity experiments, medical preservations, infrared sensors, and many laboratory applications. However, commercial cryostats are usually very expensive because they often require liquid nitrogen or liquid helium to achieve cryogenic temperatures. This makes them less accessible, especially for education purposes. Therefore, our project focuses on designing a low-cost mini cryostat by utilizing recycled materials. The main objective is to demonstrate the basic principles of cryogenic cooling in an affordable and sustainable way. Besides understanding the scientific concept behind a low-temperature system, this project also promotes environmental responsibility by reusing materials that would otherwise become waste. Next, we would like to discuss the importance of cooling technology. At low temperature, the thermal energy of a particle decreases, causing molecular motion to slow down significantly. This principle is essential in many areas of science and technology. Cooling technology has many important applications. For example, in medicine, low temperature are used for vaccine preservation and biological sample storage. In electronics, cooling helps prevent overheating and improve the performance of semiconductor devices. In physics research, particle detectors and superconducting systems also require extremely low temperature. Despite these important applications, traditional cryogenic systems are often expensive and difficult to access, especially for students and educational institutions. Therefore, our mini cryostat serves as a practical and affordable alternative for learning about cryogenic systems. By using recycled materials, we are also able to reduce the overall cost and encourage sustainable engineering practices.
Physics principle. First, the basic cooling concept. Cooling is simply the process of removing heat energy from an object, and heat naturally flows from warm areas to cool areas. So, in our cryostat, we create very cool environment around the inner chamber. This cool environment absorbs heat from inside, which causes the temperature to drop. Second, the heat transfer equation. The amount of heat we remove is given by Q equal mCT. Q is the heat removed, m is the mass of the substance, C is the specific heat capacity, which depends on the material, and T is the temperature change. This equation helps us understand how much cooling we actually need. Third, the three ways heat enter the chamber. Heat can get in through conduction, convection, and radiation. Conduction is heat traveling through solid walls. So we use polystyrene or styrofoam, which is poor conductor. Convection is heat traveling through moving air. So we seal the chamber tightly to stop air from flowing in. Radiation is heat traveling as infrared wave, so we use light color or reflective surface on the outside to reflect heat away. Fourth, why we use ice and salts. Ice alone melts at 0 degrees Celsius, but when we add salt, it lowers the melting point below 0. This is called freezing point depression. The ice-salt mixture becomes much colder than ice alone, so it can absorb more heat from the chamber. And fifth, the thermal equilibrium. The temperature inside drops until it reaches a point where the rate of cooling equals the rate of heat leaking back in. That lowest temperature is the balance point. Once the ice-salt mixture runs out, the temperature slowly rises again. Next,
I will explain the design concept and materials used for our mini cryogenic cooling chamber. Our main objective was to build a low-cost, portable, and sustainable cooling chamber that can achieve temperature below 0 Celsius without using liquid nitrogen. So for the outer structure, we use a recycled polystyrene box because polystyrene is a very good thermal insulator. It has low thermal conductivity, meaning it slows down heat transfer from the surrounding into the chamber. So this will help maintain a lower temperature for a longer period. And inside the chamber, we use a recycled aluminium container. Aluminium has a high thermal conductivity, which will allow heat from the sample to be transferred efficiently to the cooling medium. This will increase the cooling rate of the sample placed inside. The cooling source is an ice-salt mixture. Normally, ice melts at 0 Celsius, but when salt is added, it lowers the freezing point of water through freezing point depression. So as the ice melts, it absorbs latent heat of fusion from the surrounding, which causes the temperature of the mixture to drop below 0 Celsius, which depends on the salt concentration. So to minimize unwanted heat transfer, we seal the chamber using foam or rubber insulation, reducing air leakage and limiting heat entering by convection. So a temperature sensor or thermometer was installed to continuously monitor the chamber temperature throughout the experiment. So overall, this design emphasized affordability, simplicity, and environmental sustainability by using recycled materials while still demonstrating the fundamental principle of heat transfer and thermodynamics.
Next is procedure. Assemble the mini cryostat and install temperature sensor. Place the temperature around in the chamber and then seal the chamber tightly to reduce heat entry. The temperature was recorded for every 5 minutes and the observed temperature increases over time. The cooling effectiveness depends on the insulation quality and cooling material quantity. The temperature eventually rises due to external heat transfer, and the result conforms with thermodynamic and heat transfer principle.
Hello everyone. Now I will explain the data collection. The initial temperature is 26.50 Celsius and the final temperature of our project is 2.94 Celsius. Now, this slide shows the relationship between the temperature and time during the cooling process. The table on the left is the list of the recorded temperature values at 5 minutes interval, while the graph on the right is illustrated the same data visually. At the beginning of this project, after 5 minutes, the temperature was 25.06 Celsius. As the time increased, the temperature gradually decreased, and after 20 minutes, the temperature is 21.69. Between 30 and 35 minutes, as you can see there, the temperature experienced a larger decrease, which is from 20.0 Celsius to 16.31 Celsius. That show that indicate a faster cooling rate during this period. After that, the rate of cooling became slower, which is from 40 minutes onward, the temperature decreased only slightly, reaching 13.19 at 1 hour experimental. Overall, the graph demonstrates a negative relationship between temperature and time, so that as time increases, the temperature will decrease. The slower rate of cooling near the end suggests that the sample is approaching thermal equilibrium with its surrounding, where the temperature difference between the sample and the environment becomes smaller. In conclusion, the result that we gain confirm the expected cooling behavior where heat is lost rapidly at the beginning and more slowly as the object approaches room temperature. We've successfully get the lowest temperature, which is 2.94 Celsius.
In conclusion, our mini cryostat successfully demonstrated the basic principles of cryogenic cooling using simple and recycled materials. The temperature was reduced significantly, showing that the design is effective for educational demonstrations while remaining low cost and environmentally friendly. Although it cannot achieve the extremely low temperatures of commercial cryostats, it provides a good understanding of heat transfer, insulation, and cooling concepts. For further improvements, the ice and salt mixture should be mixed more thoroughly to ensure better contact between the two materials, resulting in more efficient and uniform cooling. Better sealing and improved insulation materials could also help reduce heat leakage and further improve the cooling performance. And that's all from us. Thank you for watching.